Swayam Prabha. Digital India. Educated India.
All right, so good morning, good afternoon, and welcome back. This is a course on analysis and design of rigid pavements. In the previous lectures, we had an introduction to what are rigid pavements, what are the benefits of rigid pavements, what are the disadvantages of rigid pavements. We then looked at what are the different layers in rigid pavements and what are the different types of rigid pavements. We learned about something called JPCP, jointed plain concrete pavements, which are the most common types of rigid pavements. We learned of something else called JRCP, reinforced concrete pavements, which are used fairly less. We learned about something called CRCP, continuously reinforced concrete pavements, which are much more expensive, but under ideal conditions for certain applications, they are of great value as a pavement. They can take a large amount of heavy load with almost no maintenance. And then we learned about something called PCP, which is pre-stressed concrete pavements, which is not often used in highways, but sometimes in airport pavements and airport runways, they are used because they're relatively simple and quick to maintain. So, in the last lecture, we looked at what are the different materials which are used in rigid pavements. And I had mentioned there that when we talk about materials, we don't just measure any material property. We essentially are interested in knowing what is the response of a rigid pavement, and then given that response, what is the theory that we're using to characterize or calculate that response, and what material properties does that theory require us to measure. So the really, when we talk about materials, it is dictated by the theory used to characterize those materials. Now that's what we talked about in the previous lecture. Let's say we've done all that. Let's say we've characterized our materials and now we've built our pavement. Now what happens? How do we keep track of the performance of the pavement? What should we be measuring to know whether a pavement is doing well or whether a pavement needs some amount of maintenance or rehabilitation? That's going to be the topic of today's lecture, which is going to be the last lecture in module 1, and the topic is rigid pavement distresses. So today, at the end of today's lecture, what we'll be doing is you will be able to identify and explain the causes of various distresses in rigid pavements. So we'll go through a large number of typical distresses which are seen. We'll see what they look like, how we can measure them, and we'll try to understand what is the mechanism and what is the reason that they happen. In addition, I'll define something called IRI, which is the International Roughness Index. It's not a distress. It's actually a sort of composite value which is used, but a composite value which takes into account many different distresses. But for historical reasons, it's a very important value that we do need to know about and that we do need to know how to calculate. And I'll talk a little bit about what those historic reasons are. So that's going to be a topic of today's lecture. Now, let's have a preview of a little bit of a recall of our first lecture where we talked about the fact that pavements are designed to fail, that pavement design philosophy is of controlled failure over time. So, I had shown the picture on the left over here during the first lecture. Now, this is a building which I had seen has basically collapsed. The lower level, the ground floor is basically just collapsed in and it's no longer safe for anybody to live inside of it. I had mentioned that the building was not designed to do this. If you ever saw a building, and I hope none of you ever see such a building, but if you ever see a building like this, no engineer designed this to actually happen. This was an unfortunate event that should not have happened. Now, let's look at another picture, which is the picture on the right. Here, this is a rigid pavement with a large amount of cracking. If you saw such a pavement and you are not a pavement engineer, maybe you think, oh, this was badly designed. This should not have been done. This pavement should not have been like this. But actually, it's possible, depending on how old the pavement is, depending on how much traffic has come on it, depending on what type of material, what type of maintenance and servicing was done. So, depending on a large variety of factors, it's possible that not only is this pavement fine, it was actually designed to be exactly like this. So, it's possible that, or whereas on the left, this building was never designed to be like this pavement on the right could have been designed to be exactly like that at the time that you saw it. So, most infrastructure in civil engineering is not designed to fail on purpose. Civil engineering structures, however, pavement engineering structures and pavements are designed to fail on purpose. So, when you see this sort of cracking in rigid pavements, it's not necessarily a bad thing. Of course, whether it's safe to drive on, whether it's comfortable to drive on, that's a different question. But it's possible that we do design for something like this. So, going a little bit deeper from what we showed in the first lecture, I had talked about the fact that if I have time on the y-axis and I plot pavement condition, we'll talk today about what pavement condition means. But if I plot pavement condition on the y-axis and time on the x-axis, then initially when I first build my road, then the pavement starts as some type of satisfactory condition, whatever that means, qualitatively or quantitatively. It starts as some satisfactory condition, and very quickly it starts to deteriorate. So initially you have a slow rate of deterioration, and then it accelerates over time. If you don't perform any sort of maintenance, the moment the pavement reaches something called a failure condition, then we say that that is the design life of the pavement. Now, the failure condition for the pavement doesn't mean the pavement has disintegrated, doesn't mean it's gone. It just means it's no longer safe or it's no longer comfortable for anyone to drive on it. Typically, we don't wait for this to occur. An agency would have something called a maintenance threshold. So you wait until the pavement reaches a maintenance threshold. Now, this is not to say that between satisfactory condition and maintenance threshold, the pavement is in pristine condition. Not at all. This may, depending on the type of road, depending on the agency, depending on the economics involved, this maintenance threshold might actually be a pretty bad road. For example, this picture I showed over here, this could actually be close to the maintenance threshold, but not going below the maintenance threshold. So when you reach the maintenance threshold, then typically some amount of maintenance or rehabilitation activity has to happen. The condition of the pavement has to go back up to satisfactory condition, and the whole process repeats, so on. So typically the pavement does last forever, even though it is designed to only serve a certain amount of service life, because we do perform some amount of maintenance once the pavement condition reaches some type of maintenance threshold. So let's ask ourselves, what is this pavement condition that we've been talking about? There are ways to quantify it, but at the heart of it, it is an empirical measure that measures the functional performance of the road. How well is the road performing its function? To which, of course, we must ask the question, what is the function of the road? Which is to take us from one place to another comfortably and safely. So how comfortable or safe is it to ride on the road? That's our question. And an empirical measure of that question, of the answer to that question, is this so-called pavement condition. Now, how do we quantify pavement condition? To quantify pavement condition, we have to understand what makes a pavement not in a satisfactory condition. So what are we looking for on a pavement that would make us say that maybe this pavement is not as good as I would like it to be? Those things which you see on the pavement which create this kind of reaction from you are called pavement distresses. Formally, a pavement distresses is an expected, which means it could be part of your design, or unexpected, which means your design didn't actually figure out that this is going to happen. So pavement distress is an expected or unexpected change in a pavement condition that leads to a decline in its functional performance. Functional performance, again, meaning the ability to drive comfortably and safely on that road. Now, I keep pointing out the term over here, functional performance, and related to that, there's another term which is structural capacity. Structural capacity you might think of as the strength of the pavement, although that's kind of a soft term that's strictly speaking from an engineering perspective that can mean many different things, but let's say broadly I mean some kind of strength. So when we talk about a decline in functional performance due to pavement distresses, that may be caused by a decline in the structural capacity. Put simply, it could be that for whatever reason, our concrete strength has decreased over time, and that's why it's developing cracks. The cracks which are formed in the concrete, those are the distresses. The fact that the distresses happen because of a decline in the strength, or maybe because of a loss of slab support, which is the subgrade or the base layer has eroded, the fact that that happened is the mechanism of the distress, but the distress is actually what we observe functionally. So the mechanism of the distress might be related to structural capacity. Sometimes it's also related to function, as we'll see, but the distress itself is always related to functional attributes of the pavement. So what are the different types of distresses? We will see in the coming slides, we will see a very large list of different types of distresses, and we'll talk in detail about the mechanism. But broadly, we should understand that there are two types of distresses. Distresses which are caused by load, and for pavement engineering, load basically always means traffic. So distresses which are caused by load, and those are meant to accumulate over time. And distresses which are caused by climate, or they're related to material. The climate or material related distresses would have occurred regardless of whether you had a high volume road or a low volume road, or maybe if you didn't have much traffic altogether for whatever reason. So that's why we have to clearly understand these two different types of distresses, because the mechanism of these two is very different. That's why we classify them differently. So in order to quantify pavement condition, we need to quantify distress. So we need to know, first of all, how do we identify a distress? If I send you out on a road, and by the way, I encourage you to do this next time you go outside. Next time you go outside and look at a road, first of all, you have to identify what type of distress am I looking at? And then you have to be able to quantify, is this high distress, medium distress, low distress? A quick way to do that is this particular book over here, and which you can freely download as a PDF from this link which I've provided. This book is developed by the US. So FHWA is the Federal Highway Administration. In the US, they have a particular program called LTPP, which stands for Long-Term Pavement Performance. So what it is they basically have instrumented a large number of sections in the United States, and over a long period of time, 20, 30, I think some sections might go out as much as 50 years, they've instrumented a large number of sections, and they are continuously monitoring its performance. They're seeing what type of distresses are developing, they're measuring its strength, they're measuring temperature. So it's a very large volume of data, which, by the way, for those of you who are interested, that data is actually freely downloadable from anywhere in the world in digital format. So the LTPP program was developed to enable researchers to have this type of performance data. And a lot of research in India actually is also informed by the data in the LTPP database. In developing the program, however, they had to have a common definition for what is a pavement distress, what is a severe pavement distress, what is a high, what is a low pavement distress, medium, etc. So they had to have a common set of definitions, which those who are going out and actually doing these measurements, they would be able to follow along a common set of standards. That procedure of developing a common set of standards for identifying and quantifying distresses led to the development of the FHWA LTPP Distress Identification Manual, the Distress ID Manual for short. So it's a very good book, and we're actually going to be going through a couple of key parts of that book. But again, it is freely downloadable. It's from the link over here. I strongly encourage all of you to open this website, download it, and read it. Very easy to read, very easy to follow along, but a wealth of information. Okay, so the book overall, the LTPP, the Highway Distress Manual, basically consists of two sections. It consists of distresses for jointed plane concrete surfaces, so that's JPCP. And in the next slide, which I'll show, there's another one for CRCP. Now, as I mentioned previously, our course in analysis and design of rigid pavements primarily is concerned with JPCP. That is the most common type of pavement. But then we talk a little bit about CRCP, and generally CRCP, the distresses and its analysis, etc., is a slight variation of what we have for JPCP. So that's why mainly we'll be focusing quite a lot of energy on JPCP, and then we'll move to a little bit on CRCP. Now, within JPCP, there are broadly 4 types of distresses that they're concerned with. The first one here, which is marked A over here, is cracking. And I think all of you who've seen a rigid pavement and you've seen some cracks on the roads, you can identify that cracking is a pretty important type of distress. But actually, there are different types of cracking. There's not just one type of cracking, there are multiple types of cracking in rigid pavements. So we will talk about in subsequent slides in today's lecture, we'll talk about what these different types of cracking are, what is their mechanism, how can we quantify their severity. There is also a certain type of distress called a joint deficiency. We will not talk too much about this in today's lecture, but in a couple of subsequent lectures from now, we'll be talking about joints and joint analysis. There we'll talk a little more about distresses that can develop in joints. So I'm leaving joints a little bit aside for today's lecture. The third type is surface defects. That's basically anything that's reducing the friction on the surface, or anything that's increasing or decreasing friction on the surface is a surface defect. Within that, we look at a very important one called polished aggregates, which is also something you'll find fairly commonly, particularly in urban roads in India. And then the last type of distress is just miscellaneous, so it can't be classified into any of these. We'll be looking at one called faulting, which actually is so important that we'll talk about it first. So we'll talk first about faulting, and then we'll move back to talk about the others. And we'll also talk about one called water bleeding and pumping, which is actually very, very relevant to India during the monsoon, and it's fairly common to see. And I'll show you a picture of it, and I'm sure all of you can relate to it once I show you that picture. Now, for CRCP, as I mentioned, for CRCP also there is a section in the manual. Again, they've got cracking, surface defects, and miscellaneous. Many of these are fairly similar to JPCP. So I'm not going to repeat them, but there is one particular one under miscellaneous, which is called punch-outs, which is somewhat more unique to CRCP. So that's why I'll talk about it separately. Okay, so let's talk firstly, as I mentioned, about faulting. There's a reason why I'm pulling out faulting out of order in the list, because it is a very, very important distress which is actually used to classify other distresses, which is why it's so important. What is faulting? Faulting is simply, it can be summarized in two words: differential deflection. Okay, so of course, because we're talking about pavements, the deflection is going to be downwards. So let's take a look at this diagram which they have over here. What we have over here is we have three slabs. In between the slabs, we have a joint. Now, it doesn't necessarily have to be slabs. What it could also be is you could have two slabs, one end you have a joint, and the other end a crack has developed. Now, what happens is that the middle slab, in this example, the middle slab actually deflects downwards. And the other slabs, they may also deflect downwards, but they don't deflect by an equal amount. So eventually what you get is you actually get a physical separation between the two. Let me draw it like this. You actually get a permanent physical separation between the two slabs, which is why we call it differential deflection. The two sides of the slab have undergone a different amount of permanent deformation, hence the term differential deformation or differential deflection. So we have this differential deflection which happens, and this differential deflection and the magnitude of this, typically measured in millimeters, this is what we call faulting. So faulting can occur at joints, so it can occur between two different slabs. It's also possible that faulting can occur inside a single slab when a crack is formed. Why do we care about faulting? Among all the distresses in rigid pavements, faulting is perhaps the most irritating one for drivers. Why is that so? There are two reasons. Firstly, drivers will instantaneously sense it, even if it's a very small amount of faulting. Typically, the faulting could be of the order of 0.1 mm, 0.2 mm. Very, very small, but even that tiny amount of faulting, when you drive over that small amount of faulting at a reasonably high speed, 50, 60 kilometers per hour, it's a very sharp bump. Everybody in the vehicle will be able to feel it. Of course, then if you're in a bus or in a lorry, you will feel an even stronger bump. So something as small as a 0.1 mm faulting can be extremely uncomfortable to a driver. And secondly, even that tiny amount of faulting actually puts quite a lot of strain on the suspension of the vehicle. So if you drive over a long distance over a highway which consists of rigid pavements with a lot of faulting, you probably will have to take your vehicle to a mechanic in the end, because some amount of damage is going to happen to it. So faulting is actually a very, very serious type of distress which occurs, and it's probably the one which people recognize first and foremost. Cracking is also important, but cracking without faulting is somewhat tolerable to a lot of drivers. But faulting, even a small amount, is highly intolerable. So that's why we talked about faulting to start with. And as we shall see, faulting actually is used to characterize other distresses also. That's how fundamental it is. So let's start talking about the other distresses. Broadly, these are related to corner breaks. These are related to cracking. So the first type of cracking is what we call corner cracking, or in more informal terms, it might be called a corner break. So here's what we have. In this diagram over here, we have a slab. Obviously, there's a joint. In the corner, then we can have a crack which develops, and the crack goes at a 45-degree angle. It's approximately 45 degrees, but it goes essentially as a shear crack. It goes at approximately a 45-degree angle, and because of that, it eventually goes from one edge of the slab to the other edge of the slab, and you have this triangular piece which is formed. What is the mechanism by which this happens? This basically happens if you look at the pavement. And so what I've drawn here is the slab. Below the slab, then you've got maybe an aggregate layer or a base layer. What happens is you might have some amount of erosion which has happened at the corner. That could happen because of moisture ingress, for example. Moisture ingress is going to happen at joints. So you might have some amount of moisture ingress which has created some kind of loss of support. You've got some erosion of the base material. And so whenever you have a vehicle going on this slab does not have any support underneath it. So it's going to be subject to very high strains. Those high strains will cause the development of this type of cracking at the corners, and that's how you'll end up getting this type of a corner crack. The severity of a corner crack, and in the picture which I have on the right, this is kind of showing a field example of what a corner crack looks like. So the severity of the corner crack is generally classified into three categories: low, moderate, and high. How do we classify them? Depends on the extent of spalling on the crack. What is spalling? So spalling is, if you have a thin crack, that's generally fine. But what happens in many cases is around the crack, you start having loss of material. Some of the aggregate comes out, some of the concrete pieces come out, and you start losing material around the crack, and you start getting some kind of a hole or a depression around the crack. That particular feature is called spalling. And that's particularly dangerous because spalling is effectively opening up the crack. You're making the crack with larger, and therefore you're allowing more moisture to ingress. And you're also creating a situation where it's not a pothole, but this is sort of the equivalent of a pothole in rigid pavements. You basically have a hole in the road, and then when drivers go on it, they feel a very strong bump on it. So based on the extent of spalling, based on the faulting which is developed at the corner. So the faulting could be between on two sides of the crack. It could also be that because of the crack, at the joint itself, you have some kind of differential deflection. So some amount of faulting could develop in the corner, and whether the corner has fully broken into two or more pieces. So it's not just that you've got this one large piece, but whether even this has become shattered. So depending on what you have. So if you have a condition where you have this corner crack, but the crack width is small, you do not have any faulting, you do not have any significant spalling, it's just remaining in one large triangular piece. That is what you would call a low severity corner break. It's not a good thing. It is a distress, but mostly drivers can drive on it. They won't really face too many issues on this. Whereas if you have a situation where you have a lot of spalling, which again is sort of a hole which has been created in the ground, where you have a lot of faulting, so drivers can experience a sharp bump. And when this corner itself has broken into pieces, so the vehicle itself starts becoming a little unstable when it's on it, that's a situation where you might call it a high severity corner break. Okay, another type of cracking is what we call durability cracking. And in short, it's sometimes just called decracking. So durability cracking is actually caused by degradation of the concrete material. So remember, corner breaks are caused primarily due to degradation of the base material as well as the presence of some type of a load. So if you don't have a load, you may not really develop any severe corner cracking. But durability cracking does not depend on the load. It depends due to degradation of the concrete material. Why is it called decracking? Well, it's called D because durability stands for D, but that's actually not the reason. It's because it looks like a D shape. So here in this image, what I have, let's look at the right-hand side image first. You have a joint over here, and you've got cracks forming in this D sort of shape all around the joints. You can see it better in the diagram which I have on the left. So for example, the first one over here, you've got a joint, and then around it, these characteristic kind of tiny cracks are forming all over, and they have this D sort of shape. This is why they're called decracking. So durability, D is not because it's durability, it's because it has the shape of D, but it happens to also be called durability cracking. So durability cracking, as I mentioned, is caused due to the degradation of the concrete material. The concrete material was not well made, it was not well mixed, it was not well laid, and therefore the material itself is starting to disintegrate. What will happen over time, as you see in the diagram on the right, over time you will start actually having loss of material. The crack will start opening up because you're losing material, and then you'll eventually get a fairly large hole very close to this joint. So the severity of decracking then is going to be related to how large that deterioration is. It depends on a variety of factors. So severity can be low, moderate, or high, depending on the crack opening width. So we do have these a crack which is on the joint, or it could be a little bit away at the joint. How large are the cracks? How much of the crack has opened? What is the area over which this decracking is happening? For example, this diagram over here, which I've just circled again, you do have decracking, but it's over a relatively small area. Whereas the one on the left here, you have decracking, which is over a larger area. So what is the area over which this cracking is happening? And most importantly for decracking, whether you have any loose or missing material, as you're able to see in the diagram over here. Whether the crack is so severe that the concrete is essentially starting to disintegrate and you're losing material rapidly, that's a condition where you would have severe decracking. So decracking then depends on crack opening width, area, and loose or missing material. If you have decracking, it's very difficult to fix decracking. Primarily, it's because the concrete is of low quality. If decracking is low severity, maybe you can put an overlay on it. But if it's high severity enough, at the end of the day, you will either have to remove the concrete, or there's a process called rubblization where you can turn the concrete into a base layer and basically construct a new road on top of it. So decracking can be avoided by making sure the concrete mix is good, making sure the quality of the aggregates is good, and it's something that has to be taken care of during the time of material design. It's not something that's related to the thickness or the load on the pavement. And the third type of cracking is a somewhat less usual type of cracking, but it is seen sometimes. It's called longitudinal cracking. Now, I should just give you a little bit of terminology on these terms, longitudinal and transverse. If I have a road, then obviously I have two directions on the road. One direction is the direction along which traffic is going. That you can think of as the longer direction of the road. That particular direction, we call that as a longitudinal direction. So the longitudinal direction is the direction along which the traffic is going. And then the transverse direction is the direction perpendicular to that, which is over here. So two directions which we are interested in pavements, longitudinal direction and transverse direction, very easy to keep in mind. Longitudinal traffic, transverse no traffic. Okay, so then we have two types of cracking which we're particularly interested in. One is called longitudinal cracking and one is called transverse cracking. How do we differentiate between longitudinal and transverse cracking? Just look at the direction along which the crack is moving. If the crack is parallel to the direction, approximately parallel to the direction of traffic, we call that longitudinal cracking. If it happens to be transverse or perpendicular direction of cracking, we call that transverse cracking. So let's look at longitudinal cracking. We'll get to transverse cracking after this. But looking at longitudinal cracking, it is somewhat rare. It is not very often that you see longitudinal cracking. It is basically a problem which happened during construction. That if you had improper construction of a longitudinal joint. So for example, if you take this diagram over here, here you've got a slab, and then next to that you would have another slab, and you would have a joint over there. If for whatever reason this joint was not constructed properly, that is either the slip form paver was not aligned properly, or if it was fixed form paving, then there was an issue with the form, or there was a problem with the slump of the material, a whole variety of reasons. But if you had poor joint construction, then you can start having a somewhat weak area along that, and so a longitudinal crack is going to form parallel to it. Another possibility, which doesn't happen as often, but sometimes it is observed, is if in case you have very high loads. Now, you would say that why don't we just design for very high loads? One problem in India and all over the world really is a situation what we call overloading. So, and we will talk about this in some subsequent lectures. There are certain specified load limits in India that an individual axle of a vehicle as well as the total vehicle, what we call the gross vehicle weight, they cannot be above a certain legal limit. However, enforcement in India tends to be somewhat weak. And I'm sure all of you have seen those large trucks which have a very large amount of material, agriculture material typically, but they have overloaded with a very large amount of material. So when those type of vehicles regularly go on the road, they can create a high stress at the surface, which in turn leads us to getting some type of longitudinal crack like this. So longitudinal cracks ordinarily are because of an improper joint construction. In exceptional cases, they can be because of very high loads. And if you as a pavement engineer are called upon to decide which is the case, you have to look at the history, either the construction history, or you have to look at the traffic history to make up your mind on that. So what do we know about the severity of longitudinal cracking? Again, like the other cases we saw, we can have low, moderate, and high severity longitudinal cracking. But how do we decide whether we have low severity or high severity cracking? It depends on three factors. It depends on the crack opening width. So for example, if we have the crack over here, how wide is the crack? That's one issue, because the wider the crack is, the more of a bump the driver is going to feel, the more uncomfortable it will be, and therefore the lower the pavement condition. We are also particularly interested in the width of spalling. So again, spalling is what you can see over here. When you have a crack and then around the crack you start to lose material, that's called spalling. The diagram we shown over here was shown here as AB and CD. We can actually measure what is the width of spalling. And the diagram shows essentially how you measure it. We go from the crack outwards to the point where we have the largest amount of material which is lost. That distance or that width is called the width of spalling. So we measure based the width of spalling, and we also check whether we have faulting. Again, this is a crack. So it's possible that across the two sides of the crack, we can have some differential deformation and therefore faulting. So depending on the presence of crack width opening, width of spalling, as well as presence of faulting and the extent of faulting, we can classify these longitudinal cracks into low, moderate, or high severity longitudinal cracks. Okay, and now let's get to probably what is the most common, most important, and most interesting from a mechanics perspective type of cracking that we see in JPCP, which is transverse cracking. Sometimes transverse cracking also has the name fatigue cracking, and it is related to the fact that we use transverse cracking in our design and analysis of rigid pavements. In that, we use something called fatigue theory. So what is fatigue in short? Fatigue is basically if I have a material and I subject to a small load. I don't subject to a very high load. I subject to a small load, but I subject to it thousands, tens of thousands, millions of times. So it's a small amount of cyclical loading leads to the develop of small cracks or small micro cracks, which eventually start growing over time. That theory of such a material and such a failure mechanism is called fatigue. And pavements, as we shall see in some lectures later, pavements and rigid pavements in particular are designed based on fatigue theory. And within fatigue theory, we generally want to see that as we have traffic, we want to see what is the amount of, for a given amount of traffic, what is the length or what is the number of transverse cracks which are developed. So that's called transverse fatigue cracking. So in order to identify whether a crack is a transverse crack, well, as I talked about last time, it's the opposite of a longitudinal crack. So if the crack is parallel to the direction of traffic, which is the longer direction of the road, that's a longitudinal crack. Perpendicular to that is a transverse crack. So here in this diagram over here, this which I've just highlighted, so if this is the longitudinal direction, that's the direction along which traffic is going, perpendicular to that is a transverse crack. Again, these are the most common type of distresses that we see. They are the ones we actually account for in our analysis and design. Similar to the corner cracks and the other phenomenon that we've seen, we would also like to classify the severity of the crack after we've identified it. And here again, the severity can go from low to high. Now, the severity is characterized identically to longitudinal cracking. That is, it is based on crack opening width. How wide is the crack? Based on the width of spalling. So in the diagram over here, you've seen here that this is the crack, and then around it, you can have some area where more material is lost, which is called spalling. And then you can measure the width of the spalling as the distance, the widest distance between the 2 points where material is lost. And also on faulting. So you have a crack over here, and on either side of the crack, you can have some amount of differential deflection, which in turn generates faulting. Now, the thing to understand about transverse cracking, that among all the other cracking, this one is the one which is most strongly related to the loading. So transverse cracks generally develop over time due to repeated loading, which basically comes from traffic. Transverse cracks are not necessarily a bad thing. We actually expect transverse crack to develop in pavements over time. What we actually measure is we're not interested whether a single slab has developed a transverse crack or not. Some slab or the other is going to develop transverse cracking over time. What we are interested in is what percentage of slabs, and that's typically over a fairly long distance, so over a couple of kilometers, what percentage of slabs have developed transverse cracking. And typically that maintenance threshold, which I talked about right in the beginning, that is the threshold at which point you should probably go back and start doing some maintenance. The maintenance threshold for transverse cracks is built on the number or the percentage of slabs which have cracked. Now, if it's an expressway, if it's a large highway, maybe the only tolerable limit there might be 10%. That if more than 10% of cracks within a couple of kilometers have cracked, then if it's more than 10%, then you probably should go back and do some amount of maintenance. Whereas if you're more on a local road where you expect low volume of traffic, many urban roads, you might be able to tolerate maybe 20, even 30% of cracks, which are slabs which are cracked. So transverse cracking is very, very inherently related to the number of repetitions, which is why it's also called fatigue cracking. And we expect it to occur, and our threshold for maintenance typically also comes from the percentage of cracks which have some amount of transverse cracking. I encourage you again, all of you, to go out on roads if you have any concrete pavements, and many cities in India do have concrete pavements. If you have any concrete pavements, be careful, don't get hit by traffic. But if you actually observe, you will most likely be able to see quite a lot of transverse cracking. But in many cases in these urban roads, because we have low volume of traffic, the width of the crack is relatively small. So it's relatively easy to drive on it, even if it's cracked. Now, there is one more type of distress, which is called polished aggregates. This has absolutely nothing to do with strength. It's not even necessarily something that is a bad material. Here is what happens. You have concrete, and then over time, because a large amount of traffic is going on the concrete, there is some friction between the tire and the road. That friction will degrade the material. So you will have a layer of concrete, and then just below the concrete, you will have aggregates. So basically right on the surface, you have a cement paste, and just below that, you have aggregates. What happens is this thin layer of cement paste over time will get polished away because you're sort of continuously subjecting it to friction. So over time, it's going to become polished, worn away with time, and then the underlying aggregates will become exposed. So this picture over here shows you an example of that, where the cement paste has been lost, but the underlying aggregates have become exposed. This particular situation is called polished aggregates. This is not necessarily a bad thing. Again, in many urban roads in India, which are maybe 20, 30 years old, you will actually see these type of conditions. If it's a low volume road, it's not too much of a problem. The problem can occur if the aggregates are relatively smooth. And again, depends on the type of aggregates. But if the aggregates are somewhat smooth and as a result of polishing, you're losing friction, and if there is rain and you have further loss in friction, then you can be creating somewhat of a hazardous condition. So you certainly don't want this type of situation to occur on highways where you're driving at high speeds and you have relatively large and heavy vehicles. But on many urban rigid pavements in India, you'll see something like this. It's not something that cannot be tolerated. And that's why they're generally there and they don't require too much work. Again, but the key is the type of aggregate. Generally, we always avoid polished aggregates or very smooth aggregates in road construction, exactly for this reason. Okay, and the last distress which I wanted to talk about for rigid pavements is called pumping. Now, pumping is basically caused by moisture ingress into the subbase layer. Let me explain how it happens. So here, what I'm drawing here, I've got a rigid pavement. So again, whenever you have a JPCP, you have a joint. So you must always draw a joint. I've got a joint over here, and below the joint, I've got a base layer. And this might be an aggregate base layer. Now, what happens is that if the joint is not properly sealed, we talked about joint sealing and the importance of joint sealing, but suppose the joint is not properly sealed, then over time what will happen is moisture is going to get in from the joint and it's going to saturate the base layer. Okay, now consider what happens. You have a load which is coming, maybe it's driving in this direction. The load is coming and driving in this direction and it's going to cause the slab to deflect a little bit. Now the load eventually will move off, will continue moving and will move to the next slab. In some cases, we call this the approach slab. And in some cases, we call this the leaf slab. We'll talk more about this in the subsequent lecture. So when the vehicle is going from the approach slab to the leaf slab, the approach slab has been pushed downwards. And then when the vehicle goes off it, the approach slab goes back up and the leaf slab is pushed downwards. This leads to a cyclical movement where you have the two slabs which are going up and down. As you have vehicles going over this joint, you have the joint moving up and down ever so slightly. If you have moisture inside the base layer, what happens is this slight movement of the slab actually generates some significant amount of pore pressure inside the base layer because you have a lot of moisture in the base layer. That pore pressure in turn ejects the water out of the joint. So what you're seeing on the left over here, this diagram, this is a crack which is formed. Pumping could happen at cracks, it could also happen at joints. But in this example, it's happening in a crack. So you have a crack where moisture has seeped in, and now you have this heavy load which has gone on it. And because of this alternating action of the approach slab and the leaf slab, pore pressure is developed inside the base layer, and that is causing the water to be ejected out of the crack or the slab. But it's not going to be just water. Fine materials, what we just call fines which are in the base layer or maybe even the subgrade layer if the moisture has gone deep enough, fine materials will also get ejected out. Eventually, at the end of the day, what you will see is your road is covered in muddy, dirty water. That water then can lead to a decrease in the friction. It can lead to a hazard, particularly for vehicles which are driving at a high speed. It can lead to one additional problem that if you have ponding of that water, if that water kind of just stays over there and a large vehicle goes out on a high speed, it can cause splashing. And so adjacent vehicles could be splashed, their vision could be impaired, and then they could reach a situation where they might hit another vehicle in front of them. So pumping is a very, very severe distress that fundamentally comes from moisture which has ingressed into the base layer or the subbase layer, even as far as the subgrade layer, because you have cracks which are formed, which have provided a means for ingress, or because joints have deteriorated and joints are not properly sealed any longer and moisture has entered. So pumping, you could think of, is basically caused by climate, namely rain. And that's why in India, when you have pumping, you will typically see it during the monsoon. We get a lot of rain in the monsoon, so the soil tends to become saturated, particularly somewhere around the middle of the monsoon. The soil tends to become saturated. It's at that point of time when you can start observing quite a lot of pumping which is taking place, particularly on highways where you have these heavy sort of loads. Once you have pumping, however, there's almost nothing that can be done in terms of fixing the problem. You essentially have to perform a reconstruction. There's no other way around for pumping. If you have these cracks and moisture, but in a low volume, that is, you don't have very heavy traffic, then you may not have pumping. So in a way, pumping is related to climate. It's related to rainfall in this case. but you also require these heavy loads in order to cause enough pore pressure to develop. So pumping is somewhere in between being caused by only loading or only being caused by climate. Pumping is not generally classified into any kind of severity classification. All pumping is bad. And if you do observe pumping, particularly on highways where heavy vehicles are expected, it is important to quickly fix the problem, typically by reconstruction. So there's no severity classification for pumping. Okay, so that is pumping, and that then concludes JPCP. See, one final thing I want to talk about CRCP. So all the distresses which I talked about in JPCP, in one way or the other, can also be observed in CRCP. So there's no particular difference between them. However, there is one unique type of distress which is called punch outs, which is only observed in CRCP. Recall that in CRCP, it's called continuous because there are no joints. As opposed to jointed plain concrete pavement, this is a continuously reinforced concrete pavement. So we have steel which is going all the way through, and there are no joints, it's continuous. But in practice, what happens is CRCP tends to develop cracking approximately every 1 meter apart. Now, because of the steel, those cracks are very, very small in their width, and so it's actually very comfortable to drive on CRCP. So if you look at CRCP, or you go back to one of my earlier lectures where I showed a picture of a CRCP, there are a series of cracks, but when you're driving on it, you will absolutely not notice anything. It's a very, very smooth ride if constructed and designed properly. So there are very tight transverse cracking which takes place. So transverse cracking is not a distress on CRCP. It's actually supposed to be there, and it does not cause any issue to driving. But here is what happens. You might have transverse cracking as you expect. But in some locations, it's possible that one of the transverse cracks is no longer parallel to all the other cracks. It might have deviated a little bit, and as a result, it ends up intersecting its adjacent transverse crack. Or, in some cases, typically due to improper construction, it's possible that a longitudinal crack has also started forming. So transverse cracks will always form, but it's possible that a longitudinal crack has also started forming. If a longitudinal crack has also started forming, or if you have this kind of diagonal or shear crack which is forming, you will have a piece of concrete which now detaches from the rest of the CRCP. And that piece of concrete can, depending on how heavy the load is, depending on how fast the traffic is moving, it can actually just fly out onto the road, hence the name punch outs. So punch outs are only formed in CRCP because it's only in CRCP where you have these regularly spaced transverse crack as part of the design. But punch outs are a dangerous situation because the concrete can actually fly out rather quickly, and you can have a pretty big hole inside the concrete. So similar as other type of distresses, we can have low, moderate, and high severity punch outs. Now that is based on the extent of spalling. For example, what you see in this diagram over here, not only do you have two transverse cracks which have intersected in this Y sort of shape, but along the cracks, now the crack width is no longer small. The cracks, a fair amount of spalling has actually happened. And so now because of that, you've got a more serious punch out, and that the loss of the materials can what can cause detachment. It is also measured by the amount of faulting. So again, you've got a punch out, and because the little piece of concrete is physically free to just pop out, in that case, you can have differential deflection in between. And so you do develop faulting. And finally, we count the number of actual broken pieces. For example, over here, you can count 3 broken pieces. The actual number of broken pieces for every kilometer or so. So these 3 things combined will help you classify whether you have a slow, moderate, or high severe punch out. Again, punch outs are only observed on CRCP. So if you are out on the field and you're asked to classify distresses, and if you see something that you suspect is a punch out, first of all, you should ask yourself, is this CRCP or not? If it's JPCP, it will not develop punch outs. But if it's CRCP, then the way to know it is you have these regularly about 1 meter spaced transverse cracks on purpose. And those are CRCP. And there, if you see this type of punch out cracking, you see longitudinal cracking, that's how you know that you have a punch out. So that was punch outs. Okay, so at this point, what we saw is, for JPCP, we saw a variety of cracking related distresses. We saw polishing. We also saw pumping. For CRCP, we saw a particular cracking related distress, which is called punch outs. These are values which can be measured, which can be objectively observed. You can quantify them, and this is how you can quantify the condition of the pavement. However, many of these are somewhat more recent. It wasn't always that we had such a sophisticated understanding of different type of distresses and different mechanisms of distresses. Once upon a time around the world, there was just a need to build a lot of roads, build them very quickly. And one would argue that need is still there in large parts of the world. In that case, you really didn't have a lot of scientific understanding on what is the condition of the pavement. There was a need to develop a quick and easy method of measuring the quality of the ride, the functional performance of the pavement, quick and easy method to measure it. In particular, around the World Bank actually sponsored quite a large number of road construction projects. Initially, after World War II, they were focused on Europe, but over time, they actually started looking at Asia and Africa. India actually is one of the largest recipients of World Bank loans in the world. So, particularly in India in the 1980s, the World Bank started sponsoring a lot of road construction. Now, like any bank, a bank is not just going to give you money. They want to check whether you've done the work properly, whether the money they've given you has actually been used for what it's supposed to use or whether it's been used for some other purposes. So the World Bank, in providing funding for road construction, also developed a method to measure the quality of that road and the quality of that construction. That method led to the development of a number which is called the International Roughness Index, or IRI. International comes from the fact that it's from the World Bank. There is another thing called a roughness index, which we're not going to talk about. That was more of an Indian usage before the World Bank gave us the IRI. Now, one thing to understand is the IRI is an index. It's a relative measure of something. It is not an actual distress. You will not be able to go out on the field and look at IRI is here and IRI is there. IRI is a number which has to be calculated. It has to be relative to something else. So it's a mathematical computation that hasn't been done. So it is not an actual distress, but an IRI is actually a combination of several distresses. For example, if I have a road which has a large amount of, let's say I've got a large amount of transverse cracking, I also have some longitudinal cracking, I have some amount of, I have joints obviously, but I also have some amount of corner breaks. IRI is going to take all of these into account. All of these distresses are decreasing the ride quality, and therefore they are decreasing the IRI. If IRI is somehow a measure of ride quality, then it's decreasing IRI. So IRI is a composite value that combines the effect of a variety of distresses on ride quality. It is not a distress by itself. Nonetheless, for historical reasons, it's very important for us to understand how it's measured and what is the good value for a road and how that is defined. Now, I should add IRI, perhaps some of you who've taken a class on flexible pavements, you've learned it there. IRI does not differentiate between flexible and rigid pavements. Of course, as we know by now, flexible and rigid pavements have very different distress mechanisms. They have different load transfer mechanisms, therefore different distress mechanisms. But again, IRI was sort of built as a quick way to measure the quality of a road regardless of what the mechanism of the road was for. And so it doesn't make a distinction between rigid or flexible pavement. So what is the International Roughness Index? How do we measure it? In order to measure it, we have to understand a concept which again the World Bank came up with, which is called a quarter car model. So here I have an image of a car. Now, for those of you who are not mechanical engineers or not very inclined towards cars, let me give you a quick summary of how a car behaves. So obviously the car has some load and obviously the car is moving at some speed. Now what happens is that the car has tires and the car is essentially held up on the tires. It is not the case that the tire is rigidly connected to the rest of the body of the car. If that were the case, that the tire and the rest of the car were rigidly connected, then every little bump on the road you would feel very strongly, and a small amount of cracking could lead to a very dangerous situation where the car basically tears apart. So what actually happens in practice is that between the tire and the car, you do have a series of springs. That is called the suspension of the vehicle. So the suspension is basically a series of springs which dissipate any kind of undulation, any kind of unevenness on the road. So if you experience some road which is a little rough, the roughness is dissipated somewhat by the presence of the suspension. Now, mathematically speaking, the suspension can be shown using what's shown over here is generally shown using what is called a spring dashpot model. So you have a spring and then you have another mathematical object called a dashpot. This allows you to create a mathematical model of the tire and the vehicle. So given that the vehicle has a certain load, given that the vehicle is driving on a road which might be rough, of course I'm showing a very exaggerated term over here, but the vehicle is driving on a road which may be rough, we can mathematically calculate if we know the parameters of the suspension. So if we know the mass M, if we know K2, which is the spring coefficient, if we know C2, which is the damping coefficient for this for this dashpot, if we somehow know these values, then we can actually calculate what would be the displacement in the suspension as the car is driving along. So given a certain road profile, we can actually calculate mathematically what is the displacement. Now, obviously, it depends on which car you're talking about. Different cars have different loads, different cars have different weights, different cars have different types of suspensions. So every car would experience a different amount of total movement of the suspension, which is why the World Bank came up with something called a standardized car. They basically specified numbers for M, K, C. They specified certain numbers to use for a standardized car. They specified that this so-called standardized car is going to be moving at 80 kilometers per hour. Obviously, because it's a problem in dynamics, the speed of the vehicle also affects the response of the vehicle. So they specified it's moving at 80 kilometers per hour. Furthermore, as you know, a car has 4 wheels. But what the International Roughness Index says is that you only examine the movement or the how the suspension of one of the 4 wheels is behaving, not all 4 of them. And that is called a quarter car model. So we have a standardized car with a standardized speed, and we take only a quarter of that. That is called a quarter car model. The International Roughness Index is as follows. We go out in the field and using a certain instrument, which is called a profilometer, we actually take the profilometer on the field and we get a profile of the road. Now, what I'm drawing here is a highly exaggerated version of the profile. This distance is actually going to be in the order of 1 or even less millimeters. So it's in the order of millimeters. So it's highly exaggerated what I've drawn over here. But using the profilometer, you can get what is the profile of the road, what is the roughness of the road, to put it in a different way. Using that, mathematically, what we can see is if our so-called standard quarter car, if our tire with everything standardized drives at 80 kilometers per hour on it, then we can calculate that over this distance that it's driving, what would be the total displacement of the suspension? The suspension will move up or down depending on the undulations in the road. We can calculate what is the total cumulative movement that suspension undergoes. Then the International Roughness Index is defined as the total accumulated suspension by the total distance traveled. Think of it another way, that if we have a profilometer and we have measured the profile of maybe 10 kilometer off-road, and using this quarter car model, we calculate that for this given profile, the suspension will move a total distance of certain amount of millimeters. Again, suspension movement is in the order of millimeters. So it will move a certain amount of millimeters at each point. Obviously, you add it up over 10 kilometers, it's going to become somewhere of the order of meters. So a total suspension movement from beginning to end over this 10 kilometers will be something of the order of meters. We take that total accumulated suspension, we divide it by the distance traveled, and that value gives us the International Roughness Index. And a typical unit, it's very important to know the units, is meter per kilometer, with the exception of in the United States or countries where they use the imperial system of units. Sometimes this might be shown, for example, in inches per mile, something like this. But in India, we will always use metric units. And so meters per kilometer is the standard unit which we use for International Roughness Index. So IRC SP 16 2019 is not a code. I'll explain in a second what SP is, but IRC SP 16 2019 is a document which provides recommendations for Indian roads on International Roughness Index. And I'll show you an example of those recommendations in the next slide. But I just want to tell you what this SP is. And maybe you've learned this in your undergraduate classes, just a bit of a revision. SP stands for special publication. A special publication is not a final code. It's a series of recommendations which don't necessarily have to be followed for a project. If you don't know anything else, it's good to follow it, but legally you may not need to follow it. Whereas a full IRC code, for example, IRC 58, which I had mentioned in a previous lecture, this is a full IRC code. This is a legal document. The tender will specify that the design has to be done as per IRC 58. So contractors and designers simply have to follow it. So a special publication is not a finalized code. You can think of it as a draft code with some useful recommendations, but they need not be followed in all cases. So IRC SP 16 2019 provides recommendations for International Roughness Index for roads in India. Here is what those recommendations look like. So if you open up SP 16, there are many tables of this type. So I'm just showing you one table to give you an idea of how to read this. This is table 3.1, which the heading says maximum permissible values for roughness of expressways, national highways, and state highways in India. Now, obviously, the type of surface, you're going to have a distinction between the two. So whether you're using a flexible pavement or a rigid pavement, which unfortunately here they call cemented, which now we understand is not the correct term, but whether you have a flexible pavement or rigid pavement, they have a distinction between that. There are 3 levels of IRI. So as we have levels of severity for distresses, we also have levels of IRI, and they are classified as good, fair, and poor. And the units of IRI in this case again is in meters per kilometer. I know there's an RI over here. Ignore that for a second. I'll talk about it briefly in the end. But the IRI value, you can see over here that if you're talking about expressways, national highways, and state highways, so the highest classification of roads that we have in India, for these type of roads, it is expected that rigid pavements have an IRI of less than 2.81. If it's a good quality road. If it's fair, then it's expected between 2.81 to 3.3, and anything above 3 is poor. So you see, the IRI goes from poor to good in a fairly short value. So greater than 3.3 makes it poor, and less than 2.1 makes it good. Pretty small range. But that is how sensitive IRI is to undulations or roughness on the road. So IRI is an empirical term. It was developed by the World Bank. It's quite an old metric actually, but it is very, very useful because it's very sensitive to ride quality. So you can very accurately quantify ride quality using IRI, and that's why all over the world it is still used in practice. One last thing you might notice that the lower limit is actually higher for rigid pavements than for bituminous pavements. To an extent, that's related to friction, with the understanding that cemented concrete roads might have somewhat lower friction, so you have to have a higher IRI. But anyway, that's not particularly important. So that's the recommended range. There is a value of RI over here, which is the roughness index. It's not the international roughness index. It's another metric which was also used in time, and SP16 still has the value. It's not important particularly for this class. So we understand that we have IRI. IRI is something that actually combines different type of distresses together to give you a composite measure of ride quality. It is not an actual distress, but for historical reasons, we almost always try to measure the IRI and quantify the IRI of the road when we're doing design or analysis of the road. And we'll see more of that in subsequent lectures. Okay, so with that, we have concluded Module 1. Module 1 was meant to be an introduction to rigid pavements. We talked about the different types of rigid pavements. We talked about why we have rigid pavements, what are the advantages of rigid pavements. We talked about what are the different materials, and within materials, we talked about what are the important methods we can use to characterize those materials, which are related to the kind of performance or response we want from the pavement. And then finally, we looked at what type of distresses are generated in rigid pavements. How would you identify them? How would you quantify them? In Module 2, we are going to talk about the analysis of rigid pavements, but we are going to talk about classical methods for analysis of rigid pavements. In many cases, those methods are no longer used. They are historical methods. But in understanding those methods, you understand a lot about the behavior of the pavement, of rigid pavements, without having to do a very large amount of mathematics, complicated mathematics in that process. So in the next lecture, we are going to introduce the most fundamental theory, which was developed over 100 years ago for the analysis of rigid pavements, which is plate theory, or in particular, medium thick plate theory. So we're going to do a couple of derivations over there and look at what is the fundamental governing equation of plates as applicable to rigid pavements. With that, we conclude Module 1.